We started section 3.4 last time, and we were looking at algorithms for addition and subtraction. We're going to take some of those algorithms that we worked with last time, and we are going to apply them to doing addition in other bases. So again, the reason, the purpose behind doing this is to put ourselves a little bit more in the position of the young children that we work with, who are coming at addition and these algorithms for addition from the first time perspective instead of from the we've been doing this for 12 years perspective, okay? So we're going to start with, let's see, which base are we working with first? Oops, base 8. All right, so we've talked about base 8 before. Just a recall for a moment, base 8 has digits from 0 to 7. Once we exceed the number of digits, right, once we get after 7, we've got to go to a 2-digit number. If we were looking at place values in base 8, we'd have the, whoops, that was not the right color. We'd have the 1's place, and then we'd have the 8's place, and then we'd have 8 squared, and so on. Okay, so everybody remembers some of those details that we encountered back in section 1. So this is an example where we are adding 3, 4, base 8, and 1, 4, base 8. I'm sorry, 1, 7, base 8. And I'd like to do it a couple of ways. We will do it for the first time with the standard algorithm, because that's the one that everybody always looks at and says, but that's the way I learned it. So we should just do it that way. And so I want to kind of give you some perspective of why that makes things a little bit difficult, especially when kids are getting involved for the first time. So on the standard algorithm, or in the standard algorithm, we start with the 1's column, right? And we add 4 plus 7 together. And if we were working in base 10, 4 plus 7 is 11. But in base 8, 4 plus 7 equals 11, it doesn't work, okay? So what is it? Well, one way to think about it is 11 units, right? I mean, that's without a doubt true. But the question is, how many do we have in terms of groups of 8? So if you have 11 units, how many groups of 8 is that? One group of 8, with how many left over? 3? Okay, so we would move over into the 1 groups of 8, because this is the 8's column, there's 1 group of 8, and we'd have 3 left over. The other thing that you could do is you could think, and this is a lot of times what kids do, right, is they count on their hands. Once they get up to a certain point, they just count up after that. So they might start with, say, the 7 here, and then after 7 we would go 8, 9, 10, 11, and once we get it to 4 on our hand, we're done, right? Well, what comes after 7 in base 8? 1, 0, 1, 1, 1, 2, 1, 3. It's 1, 3. So the 1 carries over and the 3 gets written down. Okay? So those are two different sort of ways of thinking about it. We're moving on to our next column. 1 plus 3 plus 1 is 5. So this is 5, 3. And then we have to remember to write that it's base 8. I have another method written down. I'm not super fond of it for this because of it not being real practical, but we'll do it anyway. Got the same 2 numbers. We're going to just try them again. We're going to work with this, and we're going to do scratch addition on this one. Scratch addition is typically useful when we have a longer list of numbers than just 2 numbers. It just doesn't end up being quite as necessary when we have smaller groups of numbers, but we can do it this way. So if we were doing scratch addition, the whole goal, remember, is to start in the top left corner and to add down. Once you exceed or become too large for the base system that you're in, you start over and you're counting. So let's give it a try. So we've got the number 4, right? So we do 4, and then we're going to count up on our hands. We'll do it that way. So after 4 is 5, 6, 7. There's no 8. We get to 1, 0, right? So we've exceeded the 8, and then we've got 1, 1, 1, 2. What did I do wrong? How are you going to? Yeah, no, and 1, 3. We're going to 7, not to 6. To 1, 3. All right, so we had 1, 3. So that we scratched because we exceeded the number 8 because we're in base 8, and we had 3 left over, so we write down a 3. We scratched 1 time, so we carry the 1, and then we do the same thing. 1 plus 3 is 4, plus 1 is 5. That one does not exceed 8, so we are at 5, 3, base 8. Within base 8, let's try a subtraction problem. 3, 4 minus 1, 7. All right, standard algorithm first. So, of course, the first problem is that you can't take 7 away from 4, right? There's not enough. So in the standard algorithm, what you know and love is regrouping. That's what it's actually called a lot of times on papers that come home to my house right now is regrouping. What I remember learning it as is borrowing. We borrowed things all the time, so it was always called borrowing. So either way, whichever you think about it, the whole idea is that you either regroup or you borrow from the tens column, in this case the eights column. So we take one of these eights, one of these longs, away, and there are 2 of them left. But when we borrow in base 8, how many do we borrow? 8. Plus the 4 I already have, which is a total of 12. It's 12. 8 and 4 is still 12, okay? So there are 12 single little units, little blocks, right? So imagine you took them and they were Legos and you could actually break them apart, right? And you break them all apart, and there's 8 of the little ones that used to be all stuck together in a long, plus the 4 you had originally, so there's 12. And then you're able to subtract 12 minus 7, right? So you have 12 objects and you take 7 of them away, and that leaves you with 5. And then I have 2 objects and I'm taking 1 away, and that leaves me with 1, and the subscript is 8. So it's 1, 5, base 8. The other method I'm going to show you is equal additions. Now, from last time, and I know you haven't done the homework for it, so maybe you won't remember, but do you remember what the whole goal of equal additions is? The whole purpose behind it. Told you to write it down beside it. Equal additions. No borrowing. No borrowing is allowed. So what I just did for the original problem, where I borrowed, is what's exactly not allowed. Now, the way we avoid borrowing with the equal additions algorithm is that we try to turn as many things as we need to into zeros. Everywhere where I would have needed to borrow, I'm trying to turn that digit into 0. So in particular, in the ones column on this one, can't do 4 minus 7. So I'd like to turn the 7 into a 0. What would I have to add to 7 in base 8 for it to become a 0 in the ones place? 1. Okay? What is 1, 7 plus 1 in base 8? 2, 0. It is. It's 2, 0 because I don't have a 1, 8, right? There's no 8s. But if I add a 1 to the second number, I have to add a 1 to the first number. So what is 3, 4 plus 1? 3, 5. And then I don't have any problem with the subtracting because there is no more borrowing. 5 minus 0 is 5. 3 minus 2 is 1. And this is 1, 5, base 8. Okay? So the goal is no borrowing, and the way we accomplish that goal is to turn things into zeros. Okay? All right. Along these lines, this was base 8, but maybe now you're getting a little too comfortable with base 8, so we're going to switch gears and we're going to try some base 3 stuff. Base 3 has even further limitations because it only has 3 digits, right? 0, 1, and 2. So since it only has 3 digits, we end up having to borrow and carry and everything much quicker because we run out of digits much quicker. Okay, so we are going to take a look at the numbers 1, 2, 1, 2. And 1, 1, 2, and we're going to add them together. So we will start with our standard algorithm. So in our standard algorithm, we start on the right-hand column, the ones column, and we add 2 plus 2. Well, 2 plus 2 is too big, right? So again, you've got to decide how you're going to do that. One way to do that is to simply say that's the number 4. How many 3's are there in 4? 1, and I carry a 1. And how many left over would I have after I've carried 3 of those 1s? I'd have 1 left over. Now I'm in the 3's column. 1 plus 1 plus 1 would actually be 3. 3, which is 1, 0. So I'd carry the 1 and I'd write down a 0. And then I have 1 plus 2 plus 1, which was the same as the first, which was 1, 1. So I carry a 1 and I write down a 1. And then I have 1 plus 1, which is 2. Now, some of my students in the past have felt like that, especially when they're thinking about children learning to add for the first time, that it might be useful to simply write out some of these digits, right? So if I do 0, 1, 2, what comes after 2? 1, 0, and then 1, 1, and then 1, 2. We'll write down one more. It's 2, 0 next. Okay, so if you're thinking about the numbers like this, you're thinking about them almost like a number line point of view. So for a child who wants to add 2 plus 2, you could think about starting at the 2 and adding 2 more to it, right? And then you're at 1, 1. And a lot of kids think about the addition as a number line perspective. That's not that much different than the counting on your hands perspective either, right? So that also might be a way for you to think about this and put it yourself into the position of the 6-year-olds that you're going to be working with, or maybe 5-year-olds, or maybe 7-year-olds, whatever, okay? So you're thinking about this from a number line perspective. Now, I'm not actually done with the problem because it's 2, 1, 0, 1, and then I need to put a word that says base 3 beside it, okay? If it's in a different base, make sure and write it down. All right, just for fun, we're going to do one with lattice algorithm, okay? So we'll do lattice next. I have 1, 2, 1, 2, plus 1, 1, 2. If you remember the way that lattice algorithm worked is that I create a box. Since I have a 4-digit number, I need a box that's 4 boxes wide. In my 4-digit box, I will split each of the boxes along their diagonal, bottom left to top right. And when I originally put the numbers in the box, it doesn't matter if I add left to right or right to left, okay? So if you want to add from left to right, this is 1 plus 0, which is a 1. And then I have 2 plus 1. So if you're thinking number line perspective, you could go 2, start at the 2, and move right 1, which leaves you at 1, 0. So we have 1, 0. 1 plus 1 is 2. That's fine. So there's a 2 in the bottom right-hand corner. And then 2 plus 2, which is 1, 1. Again, from a number line perspective, start with a 2 and move over 2 to the right. That would be a 1, 1. Somewhere along the way, you're going to have to extend the diagonals and add along your diagonals. And you do now have to start in the bottom right corner. So there's a 1 over here. I'll write a 1 down. 2 plus 1 is 3. So I carry the 3 over, and I write down 0 left over. 1 plus 0 is 1, and then 1 plus 1 is 2. So this is 2, 1, 0, 1, base 3. Let's try a subtraction one. Are you ready? A subtraction one. All right, so if we were doing it as a standard algorithm problem, I have 1, 0, 0, 2, base 3, minus 1, 1, 0, base 3. Now, in the ones column, it's nice. Subtraction's super friendly because 2 minus 0 is 2. But as soon as I get to the 3's column, and especially the 3 squareds column, things are not so nice. Because I can't do the subtraction directly. I have to do borrowing or regrouping, right? So let's think about what happens. I would really need to take this 0 right here, and I would need to borrow from the next column over. But there's nothing in the next column over to borrow from, right? So I'm going to keep having to move columns to the left in order to find a column that has something in it to borrow from. So I end up coming over here to this column. And when I borrow whatever the base is worth. So this system is base 3, so I will borrow 3. I decrease this by 1, so that's 0, but I borrow the 3. Then I have to borrow from that 3, making it a 2, And this 0 will become a 3 because I'm working in base 3, right? What do you do in our system? You borrow 10. Every time you borrow 10. Why? Because you're in base 10, right? Because the long, the flat, everything was actually a 10 by 10. These, they're a 3 by 3, or they're 3 long or whatever. Once I've done enough borrowing, I can do my subtracting. 3 minus 1 would be 2, and then 2 minus 1 would be 1, and this would be 1, 2, 2, base 3. So we will do equal additions next. And we have 1, 0, 0, 2 minus 1, 1, 2. Now, I'm sorry, 1, 1, 0, wasn't it? Yeah. Okay. Now, the ones column is fine. I've already got a 0 in it. It doesn't need any borrowing. There's no problems with that. But the next column over the longs column that has it's my threes column in this base, I would have to do borrowing. So that's no good. So right now, my issue is this 1 right here. What would I have to add to that 1 in the threes column in order to get it to become a 0?
2.
A 2. And the reason I know that is because 1 plus 2 in this base is 3. But 3 is written as 1, 0. So I'd have to add a 2 in the threes column, so that's a 2, 0. So we're going to add a 2, 0 to both numbers. So if I add 2, 0 to the top, I've got 1, 0, 2, 2. And I've got what? I've got a 0 here and a 0 here now. But what happens when I add 1, 1, 0 to 2, 0? 2, 0, 0. Yeah. So this 1 and this 2 add to a 0 and then carry the 1 over. Carrying a 1 over to that 1 right there would make that a 2. But notice what happens at this point. If you were to try to subtract, what would happen here? I still have an issue in this column, right? The third column from the right. I can't do that without borrowing, agreed? So what would I have to add to the 2 in the third column in order to get that to become a 0? A 1. But I'd have to add the 1 in the right place value, right? So this would be 1, 0, 0. So on my top number, this becomes 1, 1, 2, 2. What does my lower number, my bottom number, become?
1,000.
It looks like 1,000. We wouldn't say 1,000 because that would be a base 10 representation of it. We'll just say 1, 0, 0, 0. And I can subtract now without borrowing. In the fourth column, I've got 0, and then I've got 1, 2, 2. So that first 0 is not necessary. This is 1, 2, 2. And then it's base 3. So are you stressed out from the other bases? A little bit? It requires a lot of thought. You have to really stop yourself from thinking the way that you've been thinking for 12 years about addition and subtraction. I mean, really. And that's the point, okay? That's the point, is to make us stop for a minute and think about what we're doing when we do the algorithms, whichever algorithm that we're trying to do. All right, we're shifting gears just a little bit. We're going to actually look at some computational things with mental math next. Now, here's the catch about mental math. Mental math means it's math you can do how? In your head, mentally, right? The whole goal is that you shouldn't have to write anything down to do it. So if I ask you to do something mentally, the writing down stuff that you're doing is not because you need to write it to be able to do it. The writing down you're going to do is so that I can see what you're doing when I can't see in your head. Does that make sense? So if you're writing down a whole lot of work, then you're probably not doing mental math. But if you're not writing down anything, then I have no idea what you're doing. So you're going to be only writing down enough that basically lets me see inside your head on the problem. That's the goal. All right? So if you're taking a look at this first one, the mental math for this one says that we're going to be adding from left to right. So our mental math addition from left to right actually looks something like this. We're starting with the number 46. And what we're going to do is, well, I'll write it all out like that first, is that we're going to take the 46 and we're going to add basically 40 plus 30. You're adding the left-hand column. So if you were to add 40 plus 6, you would add, 46 plus 38, and you were to add 40 plus 30. What's 40 plus 30? 70. Okay, and then you were to add 6 plus 8. 6 plus 8 is 14. Do you think you could add 40 plus 30 in your head?
Yes.
Yeah, I think so. Can you add 6 plus 8 in your head?
Yes.
Yes. Do you think you could keep 70 in your head while you added the 4 and the 6 to get 14? Or the 6 and the 8 to get 14? I think you probably could. You're not keeping track of that much. Just a couple of pieces of information. And then 70 plus 14 would be 84. Okay, so if you did this problem, I think you could add a couple of digits together in your head, keep them in your head long enough to add them back together. This would be the mental math of doing left to right addition. I like the next one better. You ready? The next one's called breaking up and bridging. So breaking up and bridging is the idea of keeping the 46 as a whole two-digit number, 46. But instead of adding 38 to it, you just add 30 to it. So what's 46 plus 30? 76. And then you add the 8 to it after that. 76 plus 8 is 84. So you're adding it, you're just adding it sort of one digit at a time is almost what it feels like. It's not exactly true, but it's sort of the idea. You're adding it one place digit anyway at a time. Trading off is the next one. Trading off is very nice. Trading off is the idea of taking the numbers you're given, and it looks a lot like, oops, yeah, it was 38. It looks a lot like the equal additions algorithm. So remember with equal additions, our goal was to get some zeros in there. I mean, not exactly our goal. Our goal was to not borrow, but we did it by getting some zeros in there because they're easy to work with. That's much the goal here as well. You're kind of wanting something to have a zero in it because adding with zeros, much like subtracting with zeros, is way easier than adding with other numbers. So is there one of these numbers in the units place that's really close to 0? Yeah, the 8's pretty close to 0 or close to a 10's place, right? It is. What would I need to add to this to get the 8 to become a 0? A 2. Now, if I were subtracting these numbers, I'd add 2 to both of them. But I'm adding these numbers together. So if I add 2 to the 38, what do you think I have to do to the 46? I would have to subtract 2 from the 46. Imagine this is like balancing the budget, right? There's only so much money in your wallet. And if you spend $38 somewhere, but you get there and it actually costs $40, you got to spend $2 less in some other way, right? No swiping of cards, no nothing like that. You have to actually use the cash you have, right? It's a trade-off. You do this all the time with your time. In order to spend more time on that sieve paper, there's a trade-off. You decide you're going to spend less time somewhere else. You're trading it off. Okay, so what does this do? Well, this gives me a 44 and a 40. And I don't know about you, but 44 and 40 are really easy to add together compared to 46 and 38. What's 44 plus 40? 84. You don't even have to think about it. The addition works so much faster. Compatible numbers. All right, so what are compatible numbers? Well, compatible numbers are grouping numbers together that add together nicely. For example, if you were doing single digits, 7 and 3, they're compatible numbers, but 7 and 2 aren't. Why would 7 and 3 be compatible, but 7 and 2 aren't? Because they make 10. So compatible numbers typically make things that give you zeros. You're starting to get a pattern going on here. We like zeros. Zeros are our new best friend, that kind of stuff, okay? So we're looking for numbers that when they add together, they give us more zeros. Do you see any compatible numbers in these lists? 70 and 30 are. And 60 and 40 are. So 70 and 30 equal what? 100. And 40 and 60 equal 100. And don't lose the 50 in the middle. But now I have 100, I have 50, and I have 100 for a grand total of 250. And let me tell you what, that was lots easier than if you really physically did 40 plus 30 is 70, 70 plus 50, and all of a sudden you had to stop. Because that's not one that's easy to add together, at least not as easy as the other ones we've done. And then you get a 120, and 120 plus 70 gets really big. Right? We are at 190, then I have to do 190 and 60. The thinking process of it takes longer. So compatible numbers are nice. I'm grouping numbers together that are very friendly. Now, obviously not all numbers, if I write down a list of numbers, are going to have 70 and 30 in the list, right? Obviously. So what are we going to do if it doesn't work out that way? Well, one way we can still use compatible numbers is that we can make compatible numbers. So let's take a look at how that would work. I have 35 and I have 60 here. We could leave one of the numbers stationary and find the compatible number for the other one. Like let's say, for instance, we decide we're going to leave 35. And this is just me choosing. It's not because it's anything special. What would I have to add to 35 to get 100? 65. Now, correct me if I'm wrong, but that's almost the number I've got. How far off am I? 3. So instead of adding 35 and 68, I'd kind of rather add 35 and 65 and then just add on the 3. Because this is 100 plus 3, which gives me 103. No borrowing, no carrying, no none of these sort of regrouping things that we've done before with other pieces. All right. Breaking up and bridging. We already encountered this one, but we did it before with what operation? Addition. And now I'm going to show you how to do it with subtraction. It doesn't really work any differently. The idea is to still do it by the tens digits, or by the place values digits. So 46, instead of subtracting 38, we just subtract the 30. What's 46 minus 30? That would be 16. And then I subtract the 8 off after that, and 16 minus 8's 8. So you're just subtracting off sort of a chunk of the information at a time, instead of doing it all at once. And we've already actually seen this one. This is trading off. Again, we saw it for addition. But when we did it for addition, I told you that this was almost like equal additions, right? Well, trading off for subtractions is, notice I put the triple equals, like that means by definition this is like identically the same as. It is equal additions. It's not any different at all. It's just simply a different name, you know? When people across whoever's world we're working with in terms of mathematics come up with different methods, the idea that one person discovered or created something and no one else ever thought of it is probably not true, right? Doesn't the Bible say there's nothing new under the sun? Yeah? That happens. Like multiple people come up with things and they usually give it different names when they do it. This is one of those instances. So we've got a couple of different names for the same thing. So again, you guys know how to do this because we've been working with it. We're not going to borrow. So what would I have to add to 38 to turn the 8 into a 0? 2. And since this is equal additions with subtraction, if I add 2 to the bottom number, I also add 2 to the top. If I were working with addition, I would add 2 to the bottom number. I'd subtract 2 from the top, or vice versa. So the 38, of course, becomes the 40. What does the 48 become, or 46 become? 48. And then, of course, 48 minus 46 would be 8. All right. One more mental math strategy. This strategy is called drop the zeros. Obviously, it doesn't apply to everything because not everything has zeros. But if you do have zeros at the end of numbers, it's pretty convenient. So I have 4,600 and I have 3,400. And if I just sort of ignore the zeros, this really becomes a 2-digit subtraction problem instead of a 4-digit subtraction problem. What's 46 minus 34? 12. And then my solution is to use that 12 and to tack back on the zeros. Again, you didn't really need to write any of that down. This is mental math, right? But you're writing it down just so that I can see how you're thinking about the problem. All right, we're going to shift gears one last time. I don't know if we're going to finish. We probably will. We'll see. We still only have one section left. The last section here is not finding solutions exactly. It is computational. What is this word right here? Estimation. So please be careful when you do your homework. Please be careful when you get to the test. Highlight, star, flag yourself whenever you have keywords of things. Estimation means it's not going to be exact, right? It's an approximation. You're trying to do something that makes the math easier to do by rounding or estimating in some fashion. So this first one right here is called front-end estimation with adjustment. All right, so let's deal with the two pieces here. There's a front-end estimation and there's a with adjustment. This is a two-step process. Front-end estimation means writing down the first digit of the number and ignoring the rest, or turning the rest into zeros. So I've got 332 becomes 300, 462 becomes 400, and 225 becomes 200. So I just use the first digit and I zero everything else out. That's front-end estimation. Okay, front-end estimation is using the first digit and zeroing the rest out. 300 plus 400 plus 200, what is that? 900. Okay, so this is the front-end part. The adjustment part is not the same. The adjustment part means taking the values that are left and using compatible numbers. So basically the adjustment is that I've got now a 32, a 62, and a 25. And we're using compatible numbers with estimation. Which two of these go together and almost make 100? Yeah, the 32 and the 62. Are they exactly 100? No, but they're pretty close, right? These two added together are approximately 100. Now the 25, there's really no reason to mess with it. Agreed? Yeah, there really isn't. I mean, 25 works just as well as writing down 30. So leave it as 25, write it as 30. It doesn't even really matter. But the numbers that we have left here are 900, 100, and 25. If I then combine all those pieces together, what do I get? 1,025. Or if you really didn't like the 25 and you wanted to write it as a 30, you've got 1,030. Okay? The adjustment is looking for numbers that are nearly compatible. Grouping to nice numbers, same kind of an idea. Instead of trying to make compatible numbers perfectly, you're trying to make them approximately. So somebody give me two numbers that approximately, when combined, are compatible. 35 and 64. Is that what you said, Hannah? These two make approximately what? Approximately 100. Any others? 55. What was that? 55 and 42. And what do they approximately make, Sally? Almost 100 again, right? And either leave the 71 as 71 or change it to a 70. It really doesn't matter. This is going to be approximately 270 or 271 if you like the 271 better. It doesn't matter, okay? So whichever one you want to go with, we're at approximately 270. And just to show you that your answer can be different, this is not what I have written down on my paper. The approximation I have on my paper says 255 because I grouped the numbers differently. I chose different groupings than you guys did. But are 255 and 270 pretty close together? Yeah, they're pretty close together. All right, we have two more examples, maybe three more examples. Let's finish them up really fast. Clustering is super fun. Clustering is looking at the numbers and recognizing, and again, it doesn't work on all numbers, but it does sometimes. Look at those numbers. aren't they all about the same thing? What are they all approximately? They're all approximately 500. I'll write 500 each. So really, I have about 500 times, are there 5 of them? Yeah. This is about 500 times 5. And what's 500 times 5? 2,500. Just about 2,500. Doesn't get any faster with adding than that, does it? It really doesn't. All right, you guys know how to round. When we are rounding, first of all, if it doesn't tell you what place to round to, you get to pick. So the easiest pick here would be to round to the thousands place, agreed? When we're rounding, if the next digit over is 5 and up, we round up. If it's 4 and down, we round down. So this 7 is bigger than 5, so the 4 here will round up to 5,000. The 1 here is 4 and down, so this 3 will round down, the whole number will round down to 3,000. And then 5,000 plus 3,000 is 8,000. What if we were rounding to the hundreds? Let's do that real quick. If you were doing the 4789, you'd look at the 8, right? 8 would make the 7 here round up, so what would I get? 4,800, because the 7 would round up to an 8 for 800. This 4 would make the whole thing round down, so this 1 would stay put, rounding the whole number down to 3,100. What is 4,800 plus 3,100? 7,900, which is awfully close to the 8,000 on the other example, wasn't it? Different rounding strategy. Last one, using range. All range does is it rounds things up and it rounds things down, giving us sort of a top variable, or not variable, but a top boundary and a lower boundary. So in other words, if you were to look at 370, it's between 300 and 400, agreed? And if you were to look at 647, it's between 600 and 700. So far, so good? Range adds the lower numbers together. What's 300 plus 600? 900. And it adds the upper numbers together. What's 400 plus 700? 1,100. And it says that the answer is somewhere in between 900 and 1,100. It gives a lower bound and an upper bound. And it's actually a really good strategy for making sure that the answer you get makes sense if you're really trying to work a problem out. If I'm really working out this addition problem and I get that the answer is 2,468, that doesn't make any sense because the answer should be between 900 and 1,100.